Well, hello there, amazing people, students, lovers of chemistry out there. I'm super excited to be here with you on today's video where we get to talk about understanding and writing nuclear equations. It's been a week-long series of radioactivity thus far where we've dealt with a number of topics, and today we're looking at what nuclear equations are. So let's start off by defining the concept. A nuclear equation is like a math sentence that shows what happens when an unstable atom changes into something new. So simply put, a nuclear equation is simply a way of representing a radioactive reaction mathematically. So instead of writing it from A to Z with English, we simply use symbols and signs to denote what exactly is happening. So a nuclear equation simply tells you what particle is released, whether it is an alpha or a beta particle, and it tells you the new atom that is formed. That new atom formed is called the daughter nucleus, and the parent or the atom that you started with that underwent the nuclear radiation is called the parent nucleus. So think of it as the before and after story of a decaying atom. So the nuclear equation tells you what happened or what was happening before and what happened after the nuclear reaction took place. All right, now that we have defined what a nuclear equation is, there are actually some steps you need to familiarize yourself with to know how to write and balance nuclear equations. So first things first is to write the symbol of the original atom. The original atom is called the parent nucleus. So for instance, let's say you're dealing with uranium. Uranium is written like this: 238 and 92. This over here signifies the mass number, and this over here signifies the atomic number. So you are to signify the both of them. So that we have done that, now we've written the symbol of the original atom. Then the next thing to do is to determine the type of decay, whether it is an alpha decay, a beta decay, or a gamma decay, and then write the symbol of the particle that is released. So for instance, now let's say I have the original atom to be uranium, and then uranium is undergoing an alpha decay. If I want to write the nuclear equation, I would denote the mass number of uranium, which is 238, and the atomic number, which is 92. And then I will show the alpha particle that is being released. I've denoted it over here. And then I will show the new element or atom that is formed. The new element or atom that will be formed now will now be thorium. Thorium has the mass number of 234 and the atomic number of 90. Now, how did I know that it was thorium? I knew because of this atomic number over here. The atomic number is 90. And in chemistry, on the periodic table, every element has a unique atomic number. And the only element that owns the atomic number 90 is thorium. So that's why we have thorium over here. So that's how you write a nuclear equation. And then the next thing to know is to know how to find the daughter nucleus. I told you the daughter nucleus is the final product after the radioactive decay has taken place. So you find the daughter nucleus by subtracting the mass and the atomic numbers of the particle from the original atom. So here is what we mean. Let's say the original atom, as we saw in the previous slide, is uranium. So we have the mass number 238 and the atomic number 92. So if we want to know what the daughter nucleus will be, let's name it X now, for instance, and let's show the alpha particle that was released. So they said subtract the mass and the atomic numbers of the particle from the original atom. The particle is helium atom or alpha particle, whichever one you want to call it. So they are simply saying that we are to subtract the mass number, which is 4, from the mass number of the original atom, which is 238. So 238 minus 4 will give us 234. And we are to subtract the atomic number, which is 2, from the atomic number of uranium. That's 92 minus 2, that gives us 90. So the element now becomes thorium, because thorium is the only one that owns 90 as the atomic number, and with a mass number of 234. So after you have done this, you are to check that both sides are balanced. The mass numbers must be equal on both sides, and the atomic numbers must be equal on both sides. So that means when you take the mass number on the left side, which is 238, it must be equal to the sum of the mass numbers you have on the right side. On the right side, we have 234 and we have 4. When you add the two of them together, it gives you 238. The same thing goes for the atomic number. On the left side, we have 92, and on the right side, we have 90 plus 2, which gives us 92. So you can see the equation, or the nuclear equation, is balanced. So now that we have known what a nuclear equation is, that moves us into the next thing we want to talk about. That is the decay series. What exactly is the decay series? Okay, the decay series is simply a sequence of nuclear reactions where an unstable nucleus undergoes multiple decays, that is more than one decays, until it becomes a stable element. Now think of it like this. One atom decays and it becomes another stable atom, which decays again until it finally becomes stable and non-radioactive. So let's say you have a big atom like this. It is unstable and it is radioactive. So through radioactivity, it decays and becomes a smaller atom, but that smaller atom is still unstable. And because it is unstable, it undergoes another radioactive decay, which becomes smaller yet again, which happens again until eventually we attain a small atom that is non-radioactive and stable. Now, the combination of this series of radioactive decays that we have is what we call the decay series. Did you understand what was just taught? I'm sure you did. If you did, please like, share, and subscribe. Now, why does this happen? It happens because some radioactive elements are very heavy, elements like uranium and thorium, and they are too unstable to decay all at once. So they have to go through a chain of steps, losing particles along the way until they land on a stable form. Take for instance uranium. Uranium has a mass number of 238 and an atomic number of 92. This is a very huge atom. So for it to break down and become stable, it doesn't just undergo one radioactive decay. It has to happen time and time and time again until it becomes stable. I'm sure you understood what I just said. Alright, so we have the first real life example of a decay series, which is the uranium-238 decay series. Okay, this 238 over here is showing us the mass number of uranium. Uranium is a naturally occurring radioactive element, and it doesn't decay in one step. Instead, it goes through a series of 14 steps before becoming lead, which is stable. And the lead isotope that is stable is the one with the mass number of 206 and an atomic number of 82. Alright, so now that we have seen what the decay series pertaining to uranium stands for, here are some sample stages in that decay series. It undergoes alpha decays, it undergoes beta decays, a series of many alpha and beta decays. Each decay in the series forms a new isotope or element, and the process keeps going on until stability is reached. For the first alpha decay, you can see uranium converted into thorium, and then thorium converted into a new element with the symbol Pa. Pa here stands for protactinium. Alright, so the process went on and on until they formed lead. So let's see this uranium decay series in depth and see if we can solve a question pertaining to it. But before we do that, let's see the steps involved in solving a nuclear decay series. The first thing you are to do is to start with the parent nucleus and then identify each decay step. If it's an alpha decay, identify it. If it's a beta decay, identify it as well. And then after each step, calculate the new mass and atomic number. So if it's an alpha decay, the mass number reduces by 4 and the atomic number reduces by 2. If it's a beta decay, the mass number stays the same, but the atomic number increases by 1. So let's see if we can solve a question pertaining to this. So we have a question on the screen right now that says uranium-238 undergoes 8 alpha decays and 6 beta decays. What is the final product? So step number 1, we write the symbol of the parent nucleus, which is uranium. It has a mass number of 238 and an atomic number of 92. So now that we have it, let's deal with each set of decays one after the other. So we have 8 alpha decays. 8 alpha decays simply tells us that we have 8 alpha particles that have been released. And one alpha particle has a mass number of 4 and an atomic number of 2. So 8 alpha particles tells us that we now have a total mass of 8 times 4 and an atomic number of 8 times 2. 8 times 2 gives us 16 and 8 times 4 gives us 32. That tells us that uranium's mass number 238 will reduce by 32 and the atomic number 92 will reduce by 16. 238 minus 32 will give us 206, and then 92 minus 16 will give us 76. All right, now so after the 8 alpha decays, we have an unknown element with a mass number of 206 and an atomic number of 76. And then they said 6 beta decays. Remember, each beta decay leaves the mass number the same, but the atomic number increases by 1. So if we have 6 beta decays, that means we have 6 times 0, and then we have 6 times 1. So for the mass number, we have 0 added to it, and for the atomic number, we have 6. So it means this element, which is unknown, still retains its mass number 206, but we now have 76 plus 6 as the new atomic number. 76 plus 6 gives us 82 as the new atomic number, and the mass number remains the same. The element that has 82 as its atomic number is lead, Pb. So the new element that is formed is lead 206. So that's how the decay series comes into play. I'm sure you saw how all the steps were carried out. If you're enjoying this lesson, please do well to like, share, and subscribe. Now, why do the decay series matter in radiochemistry or radioactivity? First of all, the decay series are used in radiometric dating, that is calculating the age of rocks, bones, fossils, and all of that. It also helps us understand radioactive waste and how long it remains dangerous. And then it teaches us how elements can change form over time. In fact, we saw how uranium changed into lead after a period of many radioactive decays taking place. So here is a brief recap table for you to remember all we talked about throughout this video. We have the decay series. First of all, the decay series is simply a chain of decays from radioactive to stable nuclei formed. And then we have the uranium decay series. It is one of the most well-known decay series known to man today. And then we have the alpha decay. The alpha decay is simply a radioactive decay that reduces the mass number by 4 and the atomic number by 2. And then we have the beta decay. The beta decay is a type of radioactive decay that leaves the mass number the same and then increases the atomic number by 1. And then we have the final product. The final product is also called the daughter nucleus. And it is usually a stable non-radioactive element like lead that we saw in the previous radioactive decay question that we solved. All right, so it's time to draw the curtains on today's episode. I'm sure you enjoyed every bit of it. Up next, we're going to be looking at the concept of half-life. This series has been interesting for me, and I'm sure it was for you too. So I'd like you to stay tuned up until we release the next episode, which will be coming up shortly. We'll be looking at the concept of half-life. Up until then, my name's David, and all we do here is to take the mystery out of chemistry so chemi can make history. I look forward to seeing you in the next video, and up until then, stay safe.